Now let me show the questions about I have posted below. We know that from our class it's that a number x is called an algebraic number if it satisfies a polynomial equation an xn plus an minus 1 xn minus 1 plus blah 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 plus a1x plus a0 equals to 0, while an is not equals to 0. The a0, a1, an are rational number. In this case, we can say this number is a algebraic number if it can be written at this form. Now let's see an example. Show that 2 root is an algebraic number. To solve this problem, we often let the number equals to x. So we write x equals to the root of 2, and we square both sides. We get x squared equals to 2, so that x squared minus 2 equals to 0. It's the form as we said below. So so the root of 2 is an algebraic number. Okay, this is an easy example. Now let's see an example more complicated. Example 2. Show that the root of 3 plus the cube root of 2 is an algebraic number. As we said before, we need to use x equals to this number. So x equals to the root of 3 plus the cube root of 2. And we move the root of 3 into the left side. X minus root of 3 equals to cube root of 3. We cube both sides. X minus 根号3 x minus the root of 3 cube equals to 2. And this procedure is to remove the root of cube, and we can get x cube plus x cube minus 3 root of 3x squared plus 9x minus 3 root of 3 equals to 2. And because the a0, a1, blah blah an must be rational number, so we we are now want to remove the root. So we remove the root into right side. We get x cubed plus 9x minus 2 equals to 3 root of 3x squared plus 3 root of 3. And now we square both sides so the root can be removed and we get what we want. So x cubed plus 9x minus 2 squared equals to 27x squared plus 1 squared. So x is a algebraic number. And x, so the root of 3 plus the cube of 2, the cube root of 2 is an algebraic number. We solve this problem, and if a number doesn't be written as this polynomial we said about, it's a transcendental number. Transcendental numbers. I divide this chapter into five small chapters. The first is introduction to algebra and transcendental numbers, and the number 2 is definitions and classifications. Number 3 is properties and characteristics. Number 4 is applications and significance. Number 5 is conclusion. First, let me introduce the introduction to algebraic and transcendental numbers. Origins in mathematics. The study of algebraic and transcendental numbers has its roots in the ancient civilizations, where mathematics sought to understand the nature of numbers beyond the rational and irrational. The Greeks, particularly Pythagoras and his followers, were among the first to grapple with the concept of irrational numbers, which laid the groundwork for the distinction between algebraic and transcendental numbers. Evolution of number theory. The development of algebraic number theory can be traced back to the works of mathematicians like Gauss and Galois, who studied the properties of polynomial equations and their roots. The concept of transcendental numbers emerged in the 18th century with the work of mathematicians like Euler and Hermite, who sought to prove the transcendental of certain numbers, most notably E and pi. Modern understanding. In the modern era, the study of algebraic and transcendental numbers has been significantly advanced by the use of computers and computational algorithms, allowing for the discovery and verification of new properties and numbers. Number 2 is the definitions and the classification. Roots of polynomials. Algebraic numbers are defined as the roots of non-zero polynomial equations with rational coefficients. This includes all rational numbers and all solutions to polynomial equations of any degree. The degree of an algebraic number is the degree of the polynomial, of which it is a root, and it can range from 1 to any positive integer. The example of algebraic numbers include square roots of integers, cubic roots and solution to more complex polynomial equations. The properties of algebraic numbers. Algebraic numbers are countable and they form a field, which means that any algebraic number can be expressed as a root of a polynomial with rational coefficients. Non-roots, and I also found some other statistics. First, non-roots of polynomials. Transcendental numbers are defined as numbers that are not algebraic. They are not roots of any non-zero polynomial equation with rational coefficients. This definition sets transcendental numbers apart from algebraic numbers, as they cannot be expressed in terms of the roots of polynomial equation. Examples of transcendental numbers. Prominent numbers. Examples of transcendental numbers include e, pi, and logarithms of prime numbers, which have been proven to be transcendental through various methods such as Lindemann-Welch's theorem. Properties of transcendental numbers. Transcendental numbers are uncountable and form a dense subset of the real numbers, meaning that between any two real numbers there exists a transcendental numbers. Number 3 is properties and characteristics. The algebraic properties. Algebraic numbers possess a rich algebraic structure, forming a field extension of the rational numbers, which allows for the application of algebraic techniques to study their properties. Gauler's theory. Gauler's theory plays a crucial role in understanding the algebraic properties of numbers, particularly in determining the solvability of polynomial equations and the nature of their roots. Algebraic closure. The algebraic closure of the rational number is the set of all algebraic numbers, which is a fundamental concept in algebraic geometry and number theory. And the property of transcendental properties. Irrationality and transcendence. Transcendental numbers are inherently irrational, and their properties are studied through analysis and transcendental number theory, which deals with the non-algebraic aspects of numbers. Number 2, growth rates and approximations. Transcendental numbers often exhibit interesting growth rates and approximation properties, which are studied in the context of dependent approximation and transcendental number theory. Number 3 is the Lewis theorem. Lewis theorem provides a criterion for determining the transcendence of certain types of numbers, which has been instrumental in proving the transcendence of various constants. Number 4 is its applications and significance. The number theory. Algebraic and transcendental numbers are central to number theory, where they are used to study the distribution of prime numbers and the solution to dependent equations. Algebraic geometry. In algebraic geometry, algebraic numbers are essential for understanding the solution to polynomial equations and the structure of algebraic varieties. Complex analysis. Transcendental numbers plays a role in complex analysis, particularly in the study of entire functions and their growth rates, which are closely related to the properties of e and pi. In science and engineering,